Hello, my name is David Bernhauer and I would like to introduce our topic, Analyzing Indexability of Intrinsically High-Dimensional Data using TriGen. In the first part, we will talk about our motivation. We will go through several fundamental concepts and our novel indexability indicator. In the second part, we will discuss how data distributions behave after applying the TriGen modifier. The real-world datasets for similarity search often exhibit high intrinsic dimensionality. Intrinsically high-dimensional data cannot be used for an efficient exact search. Several approximate methods have been developed to tackle this problem. Some of these methods elegantly avoid the problem of high intrinsic dimensionality by not indexing actual distances, but just permutation of pivots. The TriGen algorithm was proposed as a universal method for fast, exact, and approximate search in metric and non-metric spaces. So far, it was not analyzed as a method for intrinsic dimensionality reduction, and it will be one of our goals. In this part, we will briefly talk about fundamentals. The indexability generally refers to an ability to search efficiently in a dataset, regardless of the indexing method used. The key is the distribution of data, specifically in the case of similarity search. It is the distribution of distances. The classic indexability indicator for a metric space model is the intrinsic dimensionality, defined as the ratio of the squared mean and doubled variance of the distance distribution. Alternatively, the ball overlap factor describes the ability to partition the dataset into non-overlapping ball-shaped regions. The ball overlap factor counts ratio of overlapping and non-overlapping object pairs. The TriGen algorithm transforms the input distance space by the use of triangle generating or violating modifiers. A modifier must be a real non-negative increasing function, which preserves the ordering of distances. The triangle generating or concave modifiers inflate all the triangles into the space to become more equilateral. Then the dataset is less indexable as the intrinsic dimensionality increases. The triangle violating convex modifiers have the opposite effect, squeezing the triangles and lowering the intrinsic dimensionality for the price of retrieval error. The metric access methods use some construction of lower bounds, using the triangle inequality. In the simplest case of pivot tables, the three objects in the triangle are the query object Q, a dataset object X, and a pivot P. If the triangle is equilateral, lower bound is 0, and so the dataset object X cannot be filtered by the lower bound. On the other hand, if the triangle is squeezed to a line segment, the lower bound gets maximal, and so it's super effective for filtering. Similarly, Ptolemaic access methods use some construction of lower bounds using the Ptolemaic inequality that operates on quadrilaterals. In the simplest case, there are 4 objects in the quadrilaterals, the query object Q, a dataset object X, and 2 pivots, P1 and P2. As the quadrilaterals are more complex than triangles, there is not a single best or worst quadrilateral example for the lower bound construction, but in the best case, it provides more tight lower bound. In the second part, we will discuss our indexability indicators and analysis of data. The intrinsic dimensionality as an indexability indicator considers only distances themselves, but does not consider that some distances combinations cannot be present in triangles at the same time, which is important for the filtering by metric access methods. The ball overlap factor compensates this issue, but it cannot be easily generalized for Ptolemaic inequality or non-metric cases. Therefore, we define the triangularity to quantify the shape of triangle on a real value scale, from equilateral triangle through the line segment to broken triangle. Similarly, we define Ptolemaic to quantify the shape of quadrilateral on a scale from tetrahedron through line segment to broken quadrilateral. Definition of these terms can be found in paper. For simplicity, triangularity for equilateral triangle, respectively Ptolemaic for regular tetrahedron is equal to 1. Value 0.5 is equal to line segment, and values below does not satisfy these properties. We have analyzed several datasets and looked at the intrinsic dimensionality and retrieval efficiency using the LISA algorithm. In the table, we can see statistics for 5 selected datasets. We can see that combination of low and high intrinsic dimension datasets and the combination of real and artificial randomly generated datasets. We can notice that for datasets with high intrinsic dimensionality, it is almost impossible to index objects using the LISA algorithm. After TriGen modification, which preserves zero retrieval error, the intrinsic dimensionality is generally lower. Moreover, for datasets with high intrinsic dimensionality, the performance is better, in the case of high-dimensional vectors from AlexNet almost 2 times. The improvement is visible in distance distribution too. In this figure, we can see distance distribution for several datasets before dashed line and after solid line, applying the TriGen. For the low-dim datasets, the change is small, in contrast with high-dim datasets. In the next figure, we can see the same datasets, but this time, instead of distance distribution, the triangularity, respectively Ptolemaic on the right side, distribution. Again, we can see that high number of almost equilateral triangles, or regular tetrahedrons, can be transformed into more squeezed variants, as we expected. Finally, the TriGen allows us to specify how much triangles can be broken. Does not satisfy triangle inequality. Dependent on that parameter, represented as weight, we can show how the retrieval error and efficiency will behave. In the left figure, we can see retrieval error and efficiency based on weight. In the right figure, we can see efficiency based on retrieval error. For our experiments, we have worked with 3 lower bounds: triangle, purple, Ptolemaic, green, and combination of both, blue. At the first sight, we can declare that combination of both lower bounds improve not only the efficiency, but also the retrieval error. It indicates that using TriGen with 5% retrieval error, we can still achieve about 20% distance computations compared to the sequential scan, although the dataset was almost unindexable. In a nutshell, we can see that intrinsic dimensionality is not always sufficient to predict real performance. A high number of low distances or line segments does not imply better indexability. We can create random cluster with one outlier. The distribution will have a large number of small distances, in contrast with the outlier. TriGen can be used not only for precise and approximate search, but it can be used as tool for efficient dimension reduction with the current methods. The combination of lower bounds can help with the efficiency, but also with the retrieval error caused by broken triangles or quadrilaterals. Thank you for your attention.